Hello everybody, it's Mr. Woodward. In this video we're going to talk about the relationship between work and energy and use a really helpful visual called a work energy bar chart to show that relationship. So let's jump in. The work energy relationship is the most important relationship of the unit. As you may recall, work equals force times distance. Here's a helpful equation and is measured in the unit of joules. Okay, work is force times distance. When positive work is done, a system gains mechanical energy. And this usually happens when an object accelerates or it gains height or when a spring is compressed. So I've got a couple examples here of when positive work is being done and an object's energy increases. So notice over here we've got someone who's pushing a box up a ramp. And as they push this box, they're eventually going to move it. So maybe it starts from here and it moves eventually up to here, okay? So when we say that work is force times distance, what we're talking about is this applied force that the person is putting on the box, okay, which is being drawn here, this force, times the distance that it's being moved. So if I compared the center of this box to the center of its final position, that distance would be the distance that it's moved. And that distance that counts is always, the force that counts is always the part of it that's parallel to the distance being traveled. So you always want the force to be parallel to the distance. That's the idea. And over here we've got a cross-country skier pushing himself with his poles along the snow. And so he's got this force this way, pushing him forward. But as I was trying to mention, the only component of the force that matters is the component of the force that's actually parallel to the distance that he's moving. So if his body eventually comes kind of over this way, then the distance traveled would be from here to here. And the component of the force that matters, and I'll grab another color for this, would be this horizontal component of the force over here. Okay, so work is force times distance, and oftentimes you'll see a cosine theta thrown in at the end to suggest that it's just the component of the force that's parallel to the distance. Okay, so where would the theta be in this case? The theta would be right here. It's the angle between the horizontal and the force. Okay, but what about if an object is losing energy because of forces? Well, let's take a look here. When negative work is done, a system loses energy. So we call that negative work. Okay, up here we had examples of positive work. Down at the bottom, we're looking at examples of negative work. This usually happens when an object encounters friction or air resistance and it slows down. In short, work changes energy. Okay, so here's some examples of where we have a force that's actually pushing against the direction that the object is moving. Therefore, it slows it down and it causes it to lose mechanical energy. So here we've got the force of air resistance acting on a jet. And as the jet moves to the left, maybe its final position would be, over here somewhere. Here's the wheels. And so its displacement would be this way. But notice that the force is opposite the direction of the displacement. Okay, so this force would be doing negative work on the jet because it's slowing it down, it's causing it to lose mechanical energy. Or over here in this example on the right side, now we've got somebody who's driving a car, and that car is traveling this way. So their displacement would be in this direction. But the force is pushing in the opposite direction, this way. So I'm going to call this the force of friction. So here we would say the work being done is the force of friction times the displacement. Over here we would say the work being done is the force of air resistance times the displacement. Okay? So work is force times distance. When positive work is done, an object's mechanical energy increases. Those are these examples up here. When negative work is done, an object's mechanical energy decreases. Okay, so work changes the mechanical energy of this system of objects. The work done by external forces is related to the total mechanical energy of the initial state and the total mechanical energy of the final state this way, right? So we start with the total energy before a force is implied, plus the work that's done by these external forces will give us the amount of work that's done in some final states. And that's what I was illustrating in these pictures above, okay? And then this equation can be broken down into its pieces more specifically by showing that mechanical energy is potential and kinetic together. So the total mechanical energy of some initial state is the potential plus the kinetic, and then the total mechanical energy of the final state is the potential plus the kinetic. Okay, so what we're going to do now is we're going to look at some examples of this in graphical form that I think is going to be really helpful to you as you try to visualize how exactly work changes mechanical energy.